Okay, so good evening, everyone, and welcome to the live session of week 9 of the course Nonlinear Vibration NOC24 me54. And this course is being taught by Professor S.K. Dwivedi from IIT Guwahati, and I'm Rashya Aditi Ranjan, NPTEL PMRF TA, and I'm a PMRF scholar in the Department of Mechanical Engineering, IIT Patna. So, coming on to the overview of the week. So, this week works basically focused on the numerical techniques that are being used to deal with the nonlinear equations and which had okay so which had different numerical techniques for a different kind of operations, like for example numerical technique for a differentiation in order to find the differentiation of a particular function. So firstly, why is the numerical technique required? So as we know that if our equation is simple, even nonlinear, if it is simple, okay, so we can compute its differentiation, integration, or for that matter, its roots, or we can solve the differential equations. However, if the equation is complex, it has many terms that has power in positive, high power, high positive power, high negative power, transcendental functions like sine, cos, and then we can have exponentials, logarithmics, etc. So in that case, computing the differentiation integration, specifically finding the roots and solving the differential equation, it becomes a very difficult task. Okay, so in that case, what do? We try to use the numerical techniques in order to get the required solution. Okay, like for example, if I talk about finding the root of an equation, and I can consider a polynomial maybe as x square plus 2. Okay, so it is easy. I can compute its root. But what if I talk about a function f of x, let us say f1 of x, something like x plus cos 2x plus log of 3x, something like this. Now, if I talk about finding the root of this equation, it is a difficult task for me, right? So in this case, I try to use the numerical technique in order to find the roots, right? So that is why knowing about the numerical technique is important, right? So here we have discussed about the numerical techniques for differentiation. Then if I talk about the numerical techniques for integration, like for example, I have many techniques, like I have the trapezoidal rule, then I have the Simpson's rule, Simpson's 1/3 or 3/8 rule. Sachin, am I audible to you?
Yes, madam. Audible.
Okay, thank you.
Well,
Then we have the Gauss quadrature rule. Likewise, these are the methods that can be used for the numerical integration. Now, if I talk about finding the roots, we have the bisection method. And then we have regular falsy method, right? Then we also have this secant method, right? And various other methods. Okay, so I'll be discussing some of them when I'll take up the questions. However, these are all discussed in the class as well. Okay, so these are some techniques, and when I talk about solving of or solving differential equation, so we already know a method which is our RK4 method, right? Then we have the Euler method. We also have many other methods to solve, like RK4 method. We have RK2 method also. Then we have the explicit Euler method, implicit Euler method. Then we have the other methods also, okay, based on difference, forward difference, backward difference, these methods. So you can use anyone. See, it all depends upon the type of equation that we are dealing with, right? So there are various reasons by which a numerical method can fail. Okay, and error is one of the biggest problem with the numerical technique, be it anything for differentiation, integration, finding roots, and then that I'll show also to you that how error can come while solving the equation by numerical technique. Okay, so depending upon, like, for example, you may have a question that, okay, if there are so many types of techniques, then what technique should I use? Or if there is one technique, what is the need of other two, three techniques? So the reason is simple, that not every technique is errorless. However, it may happen that a technique or a method is good for a certain kind of equation and the other one is good for a other certain kind of equation, and it will also depend upon the error that is admissible in our system. Okay. Then logistic maps were discussed. So logistic map is basically a population growth model. Okay, herein we have xn plus 1 is equals to it was xn or 1 minus xn, something like this. Okay, so any kind of a population growth can be governed by this. So depending upon this r, we'll see that how our population is actually changing. Okay, and we say n as the generation. So what can we see over here is that if I have the data, or if I know that what is the population in the nth generation. Okay, for example, the nth generation is my current generation. Okay, and I want to know that for the second iteration. Okay, firstly, this is a discrete equation. If you can see, this is not a continuous equation. This is a discrete relation. When I say discrete, what I mean is that if I know that what is the value of x at n, okay, then I can compute the value at xn plus 1, and the value at xn plus 1 depends upon xn. Okay, so this is a discrete model. Okay, so it is related to something like that. If I know that what is the value of the population at the nth generation, then I can know what its value is going to be for n plus 1th generation, because it depends only on xn, and r is the variable which tells about the growth. Okay, so if r is, let us suppose, less than 1, you'll see that the growth after certain time it will go to 0. While if r is greater than 0, it may happen that it can have a constant value of xn plus 1. It can have period 2 cycle, it can have period 4 cycle, or likewise 8, 16, like that. Okay, and it may finally lead to chaos. And if you see, this is a very simple nonlinear equation, very simple. Okay, but it can also show you chaos. It shows you periodic doubling, period doubling, and these all things. Okay, so if there is a nonlinear system, there are high chances that it can show tremendous changes on the change of parameter. Okay, then after that, Poincare section and Lyapunov exponent was also discussed, wherein the Poincare section was used in order to reduce the dimension of the system. Like for example, if I have a periodic response, then the Poincare section would be, if you remember, it would be a point. This will be my Poincare section. While if I have two cycles, then it can have 2 points. Likewise, I have discussed it in the previous week's lecture as well, so I'll not take it in that deep. And then discussion about Lyapunov exponent were made. So Lyapunov exponent is essentially used in order to quantify the chaos. Okay, like for example, if I told you that, okay, if my Poincare section is random distribution of point in the phase plane, then that is chaos. But is it guaranteed? Is visual representative enough for telling that okay, it is chaotic. It may happen that the numerical technique that I'm solving, that I'm using to solve the equation, it may lead to error, right? And the variation of this random placement of the points in Poincare section is actually because of that error. The system is actually behaving in a periodic manner or maybe in a quasi-periodic manner. Anyways, it is not chaotic. Okay. So in that case, we compute the Lyapunov exponent. Lyapunov exponent is basically something that gives us the rate of convergence or divergence. So if my Lyapunov exponent is positive, I say that my system is chaotic. If my Lyapunov exponent is negative, then I say that my system is not chaotic. So how does it actually happens is that, for example, if I have this as xn and the value of function is as fn, or let us assume it as a 2D space, then in that case it is xn, yn. Okay. After some time, it is reaching here xn plus 1, yn plus 1. Okay, so what am I going to do? I'm going to give a small perturbation in the initial condition. Let us suppose this is small h, very small. Okay, and then I see that what is the movement, or what is the curve that it is following. So let us suppose that this is my x dash n plus 1. Okay, after a certain time, the time should be same in both. Okay, this will be my difference. Let us say this is d. So then I can calculate the Lyapunov exponent as ln of d by h. Okay, so you know logarithmic function. If my d by h is greater than 1, that Lyapunov exponent is going to be positive. Well, if my d by h is less than yeah, greater than 1, then it will be positive, less than 1, that it will be negative, right? So what does this mean? This means that if my d is greater than h, so if the initial difference that was given to the system and the final difference that was obtained after simulation, if the final distance is greater than the initial distance, then I say that my system is chaotic. See, we don't compute the Lyapunov exponent by just one cycle. We try to compute the value for n number of cycles and then we take out the average value. Okay, so this is how. So if my Lyapunov exponent is positive, then we say that my system is chaotic. Negative, then we say non. So this is a way by which we can quantify it. Okay, we can give an exact number, be it positive or negative. And this is averaged over time. Okay, so this is it about the overview. Okay, so let us now take up the questions. Okay, so the first question says that the expression which is given is the numerical technique to evaluate. Now see, if you try to visualize this, okay, what do we do when we are actually deriving a numerical technique? We have a geometrical background. Okay, we want to know that how the geometry of the system is behaving, and from that we derive the numerical technique. Okay, so if I want to visualize this equation, what is it actually saying? Okay, so first I'll plot. This is my f of x, this is my x, and let us say that this is my curve f of x. Okay, so if you see, it is actually talking about 2 points, xk and xk plus 1, which can be any arbitrary value. So let us suppose that my this is xk and this is xk plus 1. So corresponding to that, this will be f of xk and this is f of k plus 1. Okay, now if I draw an exaggerated view of this, what is this? Something like this. If I try to make a line over here. So this point is my right? And this point is my x of k plus 1, f of x of k plus 1, right? So this is how it is. So if you see, this is what? This is f of x k plus 1 minus f of xk, correct? It is the difference. And if I talk about this distance, this is actually x of k plus 1 minus x of k, right? And it is talking about the ratio of these two. Okay, it is talking about the ratio of these two, right? So if you remember, for a right angle triangle, if this is my base and this is my height and this is my angle theta, then I write tan theta is equals to, this is P perpendicular, perpendicular by base. And that is essentially my what? That is essentially my slope, right? When I compute the differentiation of a function, I essentially compute its slope only, no? Isn't it? If I am finding the slope at this point, let us say it is theta, then whatever the tan theta I'm getting, it is what? It is my slope, or it is the differentiation of that function, right? It is the differentiation of my function. So if I have something like this y and x, so when I compute dy by dx, it is essentially the slope of the function y with respect to x. And that is what we are computing over here. So what are we getting? It is actually a f dash of x k. Okay. And this gives me the formula for the numerical differentiation of a function f at a point xk. Okay. I hope that I'm able to make you understand what I'm trying to say. So this is how we actually find the numerical techniques. Okay. We actually look into the geometry of the system. What do? We actually take a very small value of h. I would say, which is our step size. Okay, here h, what I'm saying is, which is the step size is x of k plus 1 minus x of k. Okay, so for a small value of h, I'll compute the slope. Okay, so it is going to give me the slope or the differentiation at that particular point. Okay, so for a small, see, if I take the value of h very small, if you remember that we have somewhere we have studied this, that if I take a circle and if I take a very small element of this circle, it is going to be a straight line, right? Similarly, for any kind of a function f, which is a curve or maybe discontinuous or anything, we can actually find its differentiation if I take the value of h as very small. So if I look into the options of this question, the expression gives the root of a function f, no. Differentiation. Acha, there is one thing also that you need to keep in mind while computing the numerical differentiation is that whenever you are computing the value of the differentiation at a point, you should always consider a step above it. Like if you want to compute at xk, you should consider xk plus 1 and then find the difference. Okay, like in this case, we are actually finding the differentiation of function f at xk, and that is why we have considered the value of xk plus 1 and the value of the function also at xk plus 1. Okay, so the solution of this answer would be C. Okay, now coming on to the second question. Yes. So this question is related to the integration. And now again, when I talk about integration, what do? We are actually discretizing our system. Okay. So when we are discretizing our system, we are trying to find out that what is going to be the Integration. See, it comes with a very basic concept actually, that when we talk about integration of a function, like for example, if I have the axis like this, I have a function like this, what do we actually do when we integrate this function? We actually find the area under the curve. We actually find the area under the curve. This is taught in the senior secondary classes, that this is actually area under the curve. Okay, so let me just first write it. Integration of a function is area under the curve. This is what I'm going to get. Okay, so if it is area under the curve, and what if I discretize it? What if I discretize it? Which means that for a particular area, I'll take small strips like this, small strips. Okay, I'll first find the area under this, then under this. Maybe I should use a different color. Then this. Okay, then this thing, and then this. So what is essentially happening? If I take the integrations of separate of small, let us say areas, and if I sum them, sum of all the small part of the curve is equal to total area, which gives me the integration. Correct? Now this is the basic concept which we use in order to find the numerical integration. Now coming on to different type of rules and different types of methods by which we can compute. Okay, so the first one is the trapezoidal rule. Okay, so if I talk about the first one, which is the trapezoidal. Okay, so in trapezoidal rule, what do we do? For example, if I have the variation of a function like this, okay, and if I want to find the integration, what will I do? I'll just compute the area under the curve. But I want to find the numerical integration, right? So I'll have to break it. है ना? So for a small element, if I want to find the numerical integration, I use a trapezoidal rule. Now, as the name suggests, that a trapezoidal rule assumes that my variation from point, let us say that this point is A and this point is B. So it assumes that the variation of the function from A to B is a straight line. It is a straight line. This is the assumption that the trapezoidal rule follows. So if you see, this is A, this is B, this is what? This is my f of A, this is my f of B. Okay, so it assumes that it follows a straight line like this. Okay, so if you remember that the area of a trapezoid, it is given as half into sum of parallel sides into distance between them. Half into sum of parallel sides into distance between them. Half 1 by 2 area, half into sum of parallel sides, which is FA and FB. So FA plus FB, and into distance between them, which is B minus A. This gives me that what is a trapezoidal rule. Okay, so by this I get the value I. Correct? So this is what a trapezoidal rule is. Okay, so I'm not talking about the error as of now. I'll take up a numerical question and then I'll talk about the error that can come into the system. Okay, Second one is the Simpson's one-third rule. So here you see that we have considered that the variation from A to B of f is linear. It is a straight line. In Simpson's one-third rule, we assume that it is actually a quadratic interpolation. Simpson's. Here we assume quadratic interpolation instead of linear variation, right? So in this case, if I have a function f, again I have a, and then I have the variation like, let us say this is my b. So my Simpson's rule, it takes up it makes the curve something like this. Okay, so this is what my Simpson's rule say, one third. This is your f of x. Okay, so now it takes a, it also considers a point actually. See, if you want to have a quadratic interpolation, you need to have 3 points. Okay, you should have 3 points. For linear variation, you require 2 data points. For quadratic, you require 3 points. So it also considers a point in middle, a plus b by 2. So then it computes the integration I as integration of a to b f of x dx is nearly equal to, we have b minus a by 6 into f at a plus f at b plus 4 times of f at a plus b by 2. Right. If I take, I'll just add a slide. See, if you see, if I have 3 data points, then what is my h over here? If you see, what is my h over here? I have divided b minus a into 2 parts. Right. I've divided it into 2 parts. So my h is going to be what? My h is going to be b minus a by 2. Correct. So I can write this equation in terms of h as, in terms of h, I can write the equation as, here I is equal to h by 3. H by 3 because see, here I had b minus a by 6. Now b minus a by 2 I have assumed as h. So then I'm going to have h by 3. So h by 3 into, again I have f of a plus 4 into f of a plus b by 2. So this is the value of integration by the Simpson's one-third rule. Okay. Similarly, I have the Simpson's 3 by 8 rule also. Coming on to Simpson's 3 by 8 rule. Now see, here we have cubic interpolation. In the previous one we had quadratic interpolation. Here we have cubic interpolation. So by default, if I want to have cubic interpolation, I should have 4 data points, right? So in this case, I consider 4 data points, and then in that case, I write the integration as a to b f of x dx is equals to, nearly equal to 3h by 8 f of a plus 3 into a plus 2h plus f of b. And here my h is going to be what? H is going to be b minus a by, I have 4 points. So I have divided b minus a into 3 parts. Okay. So this is the Simpson's three-edge rule. Coming on to the Gauss quadrature. So Gauss quadrature is nothing but, here we assume you people must know about summation. Summation is the discrete form of integration. In integration, we apply the integration over a continuous system, and in case of summation, if we have a discrete function, if in I have a continuous function, I can directly perform the integration. If I have a discrete function, then in that case, I compute the summation, and then I compute the values, and then I apply the summation in order to sum up. Okay, so in that case, I write integration from a to b f of x dx is nearly equal to summation I is equals to 1 to n wi f of xi. Here wi is my weight, should I say. Now when I say weight, what I actually mean is when I take out the average, like if I want to take out the average of four values, I can just add the four values and divide it by 4. Well, if you see in case of Simpson's one-third or three-eighth rule, we have given a weighted average. We have, like in case of this three-eighth rule, if you see, I have divided my entire area, my entire like domain b minus a into three parts. So I have got four data points. So the first and the last one I have given a weight. If you see here, I have totally divided it into 8 parts. Okay, out of which I have given 3 by 8, 3 by 8 to the middle two, and 1 by 8, 1 by 8 to the first and the last one. Okay, so I have given the weights, different weights. So Wi is my weight and Xi is my node. Okay, so these are some ways of finding the numerical integration. So the answer to this question, which of the following numerical method may be used to obtain the integration of a function? All the four are the correct answers. Okay, all fours are the correct answer. Coming on to question number 3, which of the following numerical method may be used to obtain the root of a function? Now, what is the root of a function? If I have a function f of x, what is the root? Root of a function essentially means the value of x at which my f of x is equals to 0. Correct? I have to compute the values of x, which can be one value, which can be many different values, at which my value of the function f of x is equals to 0. Okay, so there are different ways of finding it. Now, for example, if I have a, let us suppose polynomial, I can find the root up to second, like, yes, quadratic. If I have a polynomial, for a cubic polynomial also I can find. In some cases, the biquadratic polynomial I can also find. But what if I have a equation which also has a transcendental function in it? Okay, in that case, computing the root could be a difficult task, right? That is why, and also for polynomial also, if I have a polynomial of order 10, 12, or maybe 50, in that case, what am I going to do? I cannot compute it analytically by my own. I try to find it by numerical method. Okay, so I'll talk about some methods. First one is my Newton-Raphson. Okay, so my Newton-Raphson, what does it say? It says that, okay, so let me plot the graph and I can x. Let us suppose this is my f of x. Let us suppose this is my f of x. Okay, so if you see that this is my xr, which is the root. Okay, so if you see, if my x is greater than xr, my f of x is positive. While if my x is less than xr, my f of x is negative. What does this mean? This means that there is some root in between these 2 points. Let us suppose x greater than xr. For that matter, I don't know as of now that what is xr. Okay, I'm assuming that there is a xr. Okay, so so in between these 2 points, so what am I going to do? I am going to find a relation. Okay, so the Newton-Raphson method says that you consider a point. Intuitively, you consider a point. Like for example, if I am since I have dealt with so many equations since my childhood, I have some intuition developed in me. Like for example, if I know that there is a function like x square plus 2, so I know that okay, this is a square term. It is going to be a parabolic variation, so it is going to have two roots at least. Okay, it is going to have two roots. Likewise, if I have a cubic equation, I can also intuitively get some values in my mind. Once I get the value, I try to find out the values. Like for example, if I assume there is some x naught, which I think intuitively is near, maybe near to a root. So I compute f, sorry. So I compute f at x naught, and I find out that it is positive. Then again, I find f at x naught dash, and I see that it is negative. So okay, my intuition is correct. There is a root between x naught and x naught dash. So what do I do? Now I try to apply the numerical technique, iteration. So I try to compute this. I try to compute the tangent at x naught. Now how is it going to help me out? How is the tangent going to help me out? So see, if my point is here, this is x naught, and if I try to plot a tangent at this point, what am I going to get? Something like this. Okay, so if you see that if I compute a tangent at this point, I'm going to get a value like this, x1. This tangent is going to cross the x-axis at some point x1. Now, if I get the point of point x1, I'll try to compute the value of the function f at x1, which is going to be this value. Now, if you see that what has happened, after I have taken the tangent, I found the x1. Now I have computed the value of f at x1. I see that f of x1 is positive, but its value is less than f of x naught. Correct? F of x1 is positive, but its value is less than f of x naught, which means that my x1 is now much near to the my root xr. First, I intuitively assumed that my x naught was near xr. Now I have got a new point x1 which is more near to xr. Right, now what am I going to do? I am again going to plot a tangent at x1. Now again if I plot a tangent at x1, now see this x2. See this x2 that I am getting, it is now nearly equal to xr. Okay, likewise, I start going by this iteration up till the point that my xn and xn plus 1, the variation between these two is very less. Okay, so I keep on doing the iteration up to the point where xn is nearly equal to f of xn plus 1, which means that after every iteration, the variation is not that much. It is very less. So then I can conclude that my xn is actually the root. Okay, clear? This is what a Newton-Raphson method says. Okay, I'm trying to sum it up in a brief way because I have left very less time and I have to solve some questions also. So coming on to the bisection method. So the bisection method says that similarly, like in that case, we have to compute or we have to intuitively find out some A and B such that my f at A into f at b is less than 0. Now, when I say f at a and f at b is less than 0, what I mean is that I can have two conditions. First one like this. This is going to be my b. This is going to be my a. Or I can have something like b. These are the two cases that I can have. This is f of x. So you see that f at a can be positive or negative and f at b can be positive or negative. So it should be such that it follows this. In general way, I can write f of a into f of b should be less than 0, which means that one is positive and one is negative. So the multiplication of a positive value with that of a negative value would give me a negative value. Okay, so if this is the case, then there should be a root between a and b, correct? So I assume that my root is c, which is equal to a plus b by 2. I compute the value f at c. Now I can have two cases. One is f at a, f at c less than 0, or f at b and f at c less than 0, which means that my f of c could have the same sign as that of f of b, or it could have the same sign as that of f of a. In that case, any one of both, whichever my system satisfies, I now assume that my root is now here a plus c by 2, new root c1, or b plus c by 2. Likewise, I'll start the iteration up till the point where my variation is very less. My Cn is nearly equal to Cn plus 1. The variation is very less, so I would conclude my iteration and I would say that okay, Cn is the root. Clear? Now third one is the regular falsy. So my regular falsy says that if this is my y and if this is my x, and again I have this as a and this as b, and I know that my function f of f at a is positive and f at b is negative. See, it can have the either way also. F at a could be negative and f at b could be positive also. In both ways, you will have to see. Okay. But this is a generalized formulation, so it can be applied on both. Okay, so if I know this, then in that case, if I try to draw a straight line joining these both like this, I can have a point x1, which could be close to my root. Okay, so if I compute f at x1, if it is 0, then x1 is a root, or again do the iteration. Okay, so I found x1. Now you can see that x1 is not a root. So what will I do now? Now I'll consider my x1 as b. Now I'll take this point as my new point, and then again I'll join a line, and then I'll get some x2. And likewise, I'll go up till the point xn such that xn is nearly equal to xn plus 1. And then I say my xn is the root of the system. Okay. So for this question, which of the following numerical method may be used to obtain the root of the function? All the first three options are correct. All the three options are a numerical technique to find the root of a function. Newton-Raphson, bisection method, and regular falsy. Any one you can use. Okay. Now coming on to okay. So see, I have taken a very simple function. The reason that I have taken a very simple function is because if you have a very simple function, you'll be able to compare the numerical differentiation and the analytical differentiation, and then you could know that what are the prerequisites for my numerical technique in order to get a exact solution. Okay, so see here I have taken a function f of x which is 3x square plus 4x. It is a very simple equation. I can find its differentiation. It will be 6x plus 4, right? And f dash at 1 will be 10. Now this is the exact answer that I know. But I want to see that what numerically it is going to give me. So if you remember that the numerical technique says that f dash at xn is given as f at xn plus 1 minus f at xn divided by xn plus 1 minus xn. So for now I assume that my this xn plus 1 is equal to xn plus 1, which means my xn plus 1 is equal to 1 plus 1, 2. Now let us see what answer am I getting. Okay, so if you see over here, I'll write this is for the first case where I have considered h as 1. I have my f dash at 1 as f at 2 minus f at 1 divided by 1. Now if you want to compute f at 2, what will its value be? 2 square, 4, 4 3 is 12, 12 plus I have 8, 12 plus 8 minus 7 divided by 1. What do I get? I get 13. Is it a correct answer? It is not at all a correct answer. But why is my numerical technique not giving me a correct answer? The reason is very simple. If you remember, as discussed in my first question, that we assumed that this variation, this is actually a straight line. We assumed so that it is a straight line. However, it is not necessary that it is going to be a straight line. And we can see by the equation also that it is going to have somewhat of a parabolic behavior, right? So it is never going to be a straight line. And we have assumed that for a step size of 1, it is actually having a straight line, which means that for x n to xn plus 1, the variation is a straight line, which is not true, which is not going to be true. Okay. So because if you remember, it is all based on an assumption that if I have a curve and if I consider a very small part of this curve, so then that very small part is going to behave like a straight line. But the this assumption that a very small part, I have to take this in my mind while computing the differentiation or performing any kind of a numerical technique. Okay, so now if I have to consider that this h should be a very small value, so I consider my h to be small. So let us suppose that so this is an So if you see that this equation is actually a simple equation, and that is why we could see that the solution that we obtained by numerical technique is actually not correct because we had the analytical solution. But if I have a very difficult and a very problematic equation, in that case, can I actually know whether my solution is correct or not? I cannot know. Until and unless I have an analytical solution, I cannot know. Okay, so that is why we always take some prerequisites while computing the numerical differentiation. Okay, we assume, since we know that we have to take our step size as very small, we always take it as small, and we try to do multiple numerical technique. Like for example, I'll compute for three different values of h which are very small. And if the answer is coming out to be the same for all the three values, then I can see that okay, my this value of h is correct. But if there is a variation in the values, there are very major variations, then I have to first find out that what value of h should I consider, right? What value of h should I consider in order to find out the numerical differentiation? So now second, I consider my h as 0.01. In this case, if I want to find out, my f dash of 1 will be equal to f at, right? So my f at 3 into 1.01 square minus 4 into 1.01, and then I have minus minus 3 into 1. No, this should be 4 plus 4 into 1 divided by 0.01. So if you compute this value, it would come out to be something like 0.0 1003, something like this, divided by 0.01. No, something like this, which would come out to be 10.003, something like this. Okay, so let me just check. I've done the numerical values. However, you can also check it on your own. So the value would come out as this, which is nearly equal to here 10. So my this assumption that my h is equal to 0.01 is correct, since it is giving me a correct value. Okay, so the answer would be 10. Now see, if someone would not compute the analytical value and would just apply the numerical technique, they would get the answer as 1, like sorry, A 13, but it is an incorrect answer, right? So that is what is important that we check. Now coming on to question number 5. Okay, so the question number 5 says the integration of a function from 0 to 0.12 is okay. Now this is the question of integration. Now this is again a very simple equation. So I'll first find out the analytical solution and then I'll find the numerical solution. Okay, so I have f of x as x cube minus x to the power 4 plus 2. Integration of f of x dx from 0 to 0.12 would give me x to the power 4 by 4 minus 5 by 5 plus 2x. So if you put up the limits of integration, you would have 0.12 power 4 by 4 minus 0.12 to the power 5 by 5 plus 2 into 0.12. It would give you 0.24. Okay, now if I now try the numerical technique. So if you remember, there were 2, 3 rules: Gauss quadrature, trapezoidal rule, Simpson's 1/3, Simpson 3/8. So I'll try first the trapezoidal rule. So if I try by trapezoidal rule, what do I get? So the trapezoidal rule said that it was sum of, yeah, it was the area of the trapezoid half into sum of parallel sides into distance between them, which was h by 2 f at 0, f at 0.12, and into what? This. Correct. Now this would become 0.12 by 2. F of 0. F of 0 is going to be 2 because x cube and x to the power 4 is going to be 0. So I'll have 2 plus, I'll have 0.12 to the power 3 plus 0.12 to the power 4. Not plus, it will be minus and plus 2. So if you compute these values, it would come out to be value comes out to be this. So if you see that it is nearly equal to 0.24, however, there is a minor variation. So there is some error in the trapezoidal rule. However, if you see the error is very small, reason being that my limit of integration is already very small. If my limit of integration would have been 0 to 1, the error would have been higher. Right, because if you remember, my this trapezoidal rule considers that if this is my point A on the x-axis and this is B, though my variation can be a curve, but it assumes that it is a straight line. It assumes it is a straight line. So you can see over here, this portion is my, this portion is essentially my error. However, the error is very less over here because my limit of integration is very less. Now coming on to Simpson's. So if you remember the Simpson's 1/3 rule, it says that firstly you have to divide your whole range into two parts, right? So my h would be 0.12 minus 0 divided by 2, 0.06. So my Simpson's 1/3 rule says that h by 3, f of 0, then f of 0.12, and we had 4 times of f of 0.06. Correct? This is what I got. Let me just check. Yes, f of a, 4 times of a plus b by 2, and f of b. Correct. So now if I put up the values, it would be 0.06 divided by 3, 2 plus 4 times of, we have 0.06 to the power 3 minus 0.06 plus 2. So this would come out to be 0.06 by 3 into 2 plus 4 into 2.002, 0.02. This would come out to be, which is not nearly actually, comes out to be 0.24. Okay, so I have already done the this calculations because there was no point of doing the calculation between of the class. It would just take the time. So you can also recheck the calculations if you have any doubt. Okay. So if you see my Simpson's 1/3 rule give the exact same value as that of a analytical integration. And the reason is that though my trapezoidal rule was having a very small error, but it was having an error, right? So the reason was that because in trapezoidal rule, my step size h was actually 0.12. Well, in case of Simpson's 1/3 rule, my this step size was changed to 0.06. It reduced by half. Okay, and that was the reason that the error which was present in the trapezoidal rule was actually not there in the Simpson's 1-3 rule. Okay, so now see here also in the option, if someone like for this equation, I had the privilege of computing the integration analytically. Okay, but that is not possible for every kind of equation that I have. Okay, so in that case, if I would have used the trapezoidal rule to compute the integration, and if my step size was also very high, I would have chosen the correct answer. Because see, this option also has B, which is 0.2401, which I know is an incorrect answer, right? So the answer of this question will be C. Okay, so question number 6 says that find the root of the equation using the bisection method. This is also a very easy question. You can compute the root analytically. Uh, okay, let us just compute analytic or not compute analytically. We'll compute analytically in the later stage. First, we'll try to compute it numerically. Okay, so my function is okay. So if you remember in the bisection method, what was my bisection method saying? My bisection method was saying that I intuitively have to find out some A and B such that my f of A into f of B is less than 0, which means that the value of the function at a and b would be of the opposite sign. One should be positive and the other should be negative, which means that my function, when it has traveled from a to b, it has changed its sign from positive to negative or negative to positive. That means that there should exist a point C such that f at C should be equal to 0. And for the iteration, I consider this C as the a plus b by 2, midpoint of a and b. Okay, so first I have to find intuitively. So if I consider x greater than 0, I can see that here it has x square minus 2x plus 3. And if my x is greater than 0, so I assume that, see, if I consider maybe 3.5, what will be the value at f of 3.5? Will be 3.5 square minus 2 into 3.5 minus 3. It would give me 3. It would give me 2.25. Okay, fine. It is a positive value. I should consider 2.5. So 2.5 square minus 2 into 2.5 minus 3, which would be 2.5 square, would give me 6.25 minus 5 minus 3. Okay, I guess it will be negative. Good. Now see, I have got two values, 3.5 and 2.5, such that my f at 2.5 and f at 3.5 is less than 0. So there should be a root between 2.5 and 3.5. Correct? Now what do? I apply the method of bisection. I consider a point C such that my C is equal to 2.5 plus 3.5 divided by 2. Now if I see that what is my value of f at 3, 9 minus 6. Okay, okay, very nice. So my 3 is a root. I've got as 0. This was a very easy assumption. I'll now consider some other assumption so that I can take you up to some 2-3 iterations. Anyways, I've got 3 as one of my root. 3 is one of my root. Now, if you see, this is a quadratic equation, which means it is going to have two roots. I'll try finding the other root. Anyways, if I have got one root as a real number, second one is also going to be a real number, because a quadratic equation can have complex conjugates as roots also. But if I've got one as real, then the other one is also going to be a real, right? So now if I take some other assumption, this time I'll take, okay, this would be fine. Now I consider f at 0. So if you see, f at 0 is going to be -3. And if I consider f at -1.5, so it is going to be -1.5 square minus 2 into -1.5 minus 3, which is equal to be 0.25. Now, if you see, f at 0 is negative and f at -1.5 is positive, which means there is a root between -1.5 and 0. So let us suppose first iteration, that c is equal to minus 0.75. Now, if I compute the value of f at minus 0.75, it would come out to be positive, positive, and minus something. It would come out to be this. Now, if you see, my f at minus 0.75 is negative. Okay, so my which condition is holding true? One condition should be that f multiplication, okay, f at 0 into f at minus 0.9375. One condition is this, and the other condition is f at minus 1.5 and f at, okay, okay. So see, f at 0 is negative and f at minus 1.5 is positive, and f at 0 minus 0.75 is also negative. So positive into negative. If I see, this terms comes out to be greater than 0 and this term comes out to be less than 0. So this means that my root is between minus 0.75 minus 1.5. Now again, I go for the second iteration, which says that my c is equal to, which would give me minus 1.125. Right, and if I now compute the value of f, it would come out to be, now again I have two conditions out of which one should satisfy. So if you see, now I have minus 0.75 and I have minus 1.5. I know that my function is positive for c. So my root is going to lie between what? So if you see, at 1.5 my value is positive, and minus 1.5, and minus 0.75 my value is negative. So definitely my root is between minus 0.75 and minus 1.125. Root is between minus 0.75 and minus 1.125. Again I go for third iteration. So my third iteration says that my c is equal to what? It is going to be the, again, average value, right? Minus 0.75 minus 1.125 divided by 2, which would give me minus 0.9375. Right. Now, if I compute the value of function at this point, it would come out to be minus 0.246. Okay, which is again negative. So if I remember, my this value is negative. So out of minus 0.75 and minus 1.125, whichever is positive, I'll have to take that one. So my positive is this one, which means that my root is between minus 0.9375 and minus 1.125. Now if I go to the fourth iteration, I'm going to get C as minus 1.125 minus, should come out to be. So if you see that now the C comes out to be this, you can again compute the value. It would come out to be, I guess, if this is negative, it would come out to be positive, I guess. Yes, it is going to be positive. So I'm not taking any further iteration up till now. Now see, the reason that I have taken these values is that my choice of A and B is going to actually affect how much my iteration is going to be. See, my choice of A and B over here for finding the first root was so nice that in the first iteration itself, I got the exact root. However, this is the choice that I made for finding the second root. It was such that at up to fourth iteration, I have not got the exact value. Though I've got a value which is near to my root, because if you see my equation, x square minus 2x minus 3, which I can also write as x square minus 3x minus x minus 3, sorry, plus x, which implies my roots are going to be minus 1 and 3. So my this root is should be minus 1, and you can see that we have got a value near to minus 1. However, I didn't get the exact value up till the fourth iteration. If you go up till the 10th iteration, you are going to get the exact value. Okay, but you'll have to go to the 10th iteration. See, this was a very simple equation, and going up to 10th iteration is computationally possible for us. But if I talk about very complicated equations, it may happen that we have to do maybe 1,000, 2,000, 5,000 iterations. Computationally, it is very costly. To do 5,000 iterations is going to take a lot of time. You should have a very good computer for it, right? So that is why the choice should be very nice. If I have a good choice, which would develop obviously by solving the equations, you can intuitively get relations or the values near to the root, then it becomes very easy for finding out the numerical roots. Okay, so coming on to question number 7. Okay, so in question number 7, you have a equation, and all you have to do is you have to apply the RK4 method in order to find the value at x 1.05. We already have the value of y at 1, right? So I have taken this question. It is a very simple question. I'm not going to tell you about anything about comparison, about your analytical method, numerical method, anything. This is also a very simple equation, and you can find out the value. However, I have taken this equation in order to make you understand that how the RK4 subroutine actually works, and what are we actually using in OD45. How is OD45 actually working? So that is why I have taken this equation. Though it is a very simple way which we are solving, OD45 is having many different lines in the code which talks about tolerances and whatever my the step size should be. It talks about where to stop the iteration, and everything is there. This is a very simple way. This gives a basic idea about how my numerical technique to solve the ODE works. Okay, so I have y. Firstly, what is an RK4 method? So my RK4 method says that if I have a yn is already known to me, so then I can compute yn plus 1 as yn plus 1 by 6 k1, 2 times of k2, 2 times of k3, plus K4, wherein my K1 is h into f of xn comma yn, K2 is h into f of xn plus h by 2 yn plus K1 by 2, K3 is h f of xn plus h by 2 yn plus K2 by 2, and my K4 is h into f of xn plus h, comma, yn plus K3. Okay, so I have the function. This my f function is actually y dash. My y dash is actually f. Okay, so if you see these equations, I know my h. Here I know I have to find out the value at 1.05. So my h is going to be 1.05 minus 1, which is going to be 0.05. I have h. I know my xn, I know my yn, and I can compute the values of k1, k2, k3, k4, and I just have to put it in the main equation. It's a very easy computation. Okay, so I'll just do it very fast. I think I have 3 questions remaining. Okay, see. Now if I put up the values, I have my xn as 1, I have my yn as 1. Correct? Now if I want to compute k1, which is h which is 0.05 into f of 1 comma 1, and f is x square plus 1. So what do I have to do? I have to put the value of xn and yn into it. Now you will see that my y dash is actually not dependent upon yn. So I just have to take care about the x part. So this will be 0.05 into x square, which is my 1 square plus 1, 2 into 0.05, 0.1. Okay, K2 is again 0.05 into, I have C, xn plus h by 2, which is 1 plus 0.05 divided by 2, and 0.05 divided by 2 would give me 0.025. Correct? So I'll have 1 plus 0.025 whole square plus 1, which would give me, okay, 0.10253. Again, K3 is going to be 0.05 into, I have 1 plus 0.025 whole square plus 1, which would give me again same value, 253. The last one is where I have to compute K4, and my K4 is going to be 0.05. Now I have, you see, in case of K4 I have xn plus h, which is going to be 1 plus 0.05 whole square plus 1, which would give me 0.105125. Now I have these values, I just have to put it in the main equation, which means that my yn plus 1 is going to be yn, which is my 1 plus 1 by 6 into, if I write all these values, which are going to be 0.1, the middle two values are going to be multiplied by 2 because it has more weight than the first and the last one, and plus 0.105125. This would give me 1 plus 1 by 6 into 0.615245, and this would give me the value 1.10254. Okay, so the answer of this question will be 1.10254. Now if you see, although I have taken up to 5 decimal places, I have taken the values up to 5 decimal places. If I would have not taken it up to 5 decimal places, I've taken it to up to 2 or 3 decimal places, then I would have never got the exact answer. I may have got the first answer, A. That is why it is important, both the things are important, that we take h as small and we take the values up to 4th or 5th decimal places so that we can get exact values, because even a very small error in the first stage, very small error could actually propagate to a very high error. Okay, after nth number of iterations, we say 100,000 lakhs of iteration, it is going to create a large error, and it may happen that because of this reason only my periodic behavior in by numerical integration, it is going to show chaotic behavior. Okay, the system is actually not behaving chaotically, but because of the error present in the system, error present in the computation, it is going to show false behavior. Okay, that is why it is important that you learn about these techniques. Then only you can apply it on the numerical technique so as to get the least amount of error. Okay, now Newton-Raphson technique to compute the root. So I'll just solve it. Okay. So it is already mentioned that we have to do the computation up to only the third iteration. So my f of x is this. Okay. So if you remember the Newton-Raphson technique, what it says actually? Newton-Raphson technique actually is used to solve the, see, if you remember, as I've discussed earlier also, this is what my Newton-Raphson technique says. Okay, I take this point, I take a tangent, I compute the value of x1. Okay, now after I get a value of x1, what do? I then find the second iteration, third iteration up till the point where my further iteration is not changing a significant, there is no significant change in the value of xn, and then we conclude that okay, whatever the xn is I have got is actually the root. Correct? So now so also, I'll just tell you something. You remember the way we were solving this differentiation thing, where we used to write that my f dash at xn was equal to f at xn plus 1 minus f at xn divided by xn plus 1 minus xn. Okay, so this same concept is being used to find out the relation. Okay, see, I draw a tangent over here and then I find out the value of x1, right? So if I draw a tangent and if I assume that my value at this x1 is 0, what is going to happen? But this thing is going to go to 0. Correct. Now, if I apply this in order to find out the value, what am I going to get? I'm going to get that my xn plus 1 minus xn is actually equal to minus of f of xn divided by f dash of xn. And from here, I'll get that xn plus 1 is equal to xn minus of f of xn divided by f dash of xn. So this equation is what I'll use in order to compute x n plus 1. Okay, so coming on to this question, I have the equation like x n plus 1 is equal to f of xn minus xn minus f of xn f dash of xn. So it is already given that I have to take x naught as 5. So I have my x naught as 5. So then I can compute x1 like 5 minus f at 5, f dash at 5. So f at 5, f dash is my f dash of x. It is going to be 2x minus 4. So this will be 5 minus 5 square minus 4 into 5 minus 7 divided by 5 minus 4, which is going to be 5 plus 2 by 6. So it will give me 5 point. I'm taking up to 4 decimal places. Okay. So this is my first iteration. So it is mentioned in the question that I have to go up till the third iteration. Okay. So my x2 is going to be x1 minus, now I have to compute both f at x1 and f dash at x1. So this will be 5.3333 minus 5.3333 square whole divided by 2 into minus 4. This would come out to be 5.3333 5.31666. Okay, so this is what I get as x2. Now I have to do the last iteration, which will be x3, x2 minus f of x2, f dash of x2, which would come out to be 5.3166 minus, if you put up the value, I'm directly writing the numerical values. Okay. If you'll put up the value, you can cross check all the numerical values. Okay. So it would come out to be 0.00 whole divided by 6 point. See, if you see this term, can you see how much small this term is? And if I divide it with this further, it is going to be a very small term. So you can see that somewhat up till the third iteration, my system is actually reaching its root. Okay, the variation that I'm observing is becoming less after each iteration. So this would give me 5.31662. Okay, so my answer would be this. So if you see that, I think if you'll go to the fourth iteration, you're going to get the same value, almost same value. So I think that this is almost correct answer because the variation is very less. You see the variation is on the fifth decimal place. That is on the fifth decimal place, the variation. So which is a very small variation. So this is going to be my answer. Okay, so likewise, you can use other numerical techniques also in order to find out the roots. Okay, so these are all questions which are related to the numerical techniques that I wanted to uh, discuss with you. And see, I have taken examples for particular type of method. However, if you what you can do is, for practice, like you have this equation, what you can do is just take this equation and try to apply other kind of methods like the secant method or the regular falsi method or maybe the bisection method and try to compute, like for the same equation, try to compute the roots by various techniques and see that what kind of a error every kind of technique is actually giving. So you are going to realize that depending upon the equation, some type of the technique is giving more error while some is giving less, and that is not true for every kind of the equation. Okay, so you'll have to select that for which kind of equation you should apply which kind of a numerical technique. See, it is very important that you know which kind of a numerical technique you need to choose. Like in case of a Newton-Raphson method, this is a one-dimensional system. I have the equation in terms of x only. What if I have a two-dimensional equation, that too non-linear? Usually when I have a non-linear equation, two-dimensional or maybe more, I apply the Newton-Raphson method for two-dimensional or three-dimensional system in order to get the value of the root, right? For a linear system, I can do it. For a linear system, it is easy. But for a non-linear system, that too with transcendental functions, it is very important that I learn that how the numerical techniques should be used in order to compute the roots. Okay. So now I'll go to question number 9. Okay. So my question number 9 and 10 are both numerical question. So now I'll connect with my laptop. Okay, so is my screen visible?
Yes, madam.
Okay, thank you. Okay, so now see question number 9. So the question number 9 says that the value of x and y for the given system at t is equals to 100 is. Okay, so if you see that what am I doing? I am actually applying a numerical technique to solve the equation. As I've discussed in my earlier one also, earlier equation question where I used the RK4 method to find the value. Here, question that I discussed here is you can see that I computed the value at 1.05 and I knew the value at 1. Right. Similar kind of a thing is what am I supposed to do over here? The only difference is that there I did one computation. Okay, and it was having four values of K1, K2, K3, K4. Then I had to take out its weighted average and add it in yn in order to get yn plus 1. However, if you see that for this thing, if I have t as 100, even if I take my step size as 1, which is not a correct choice actually, but even if I consider t as 1, I have to perform 100 computations, that too for a two-dimensional system. Okay, can you imagine if I try to do it on my own, it is going to take a hell lot of time. Okay, in order to get the exact value. And that too, some human error is going to occur. Okay, I'm assuming that if I am going to solve it, I'm definitely going to have some error. Okay, so taking into consideration all these things, what do? We try to find out the value by numerical integration because that would make my computation time easy. And as a engineer, my work is to find out the underlying behavior of the system rather than concentrating on the mathematics of the system. Correct. Though I can do it. I can do it mathematically. It is not impossible. It is definitely possible, but it is going to take a lot of time. Right. And as an engineer, it is my uh, work to concentrate on the underlying dynamics of the system rather than focusing on the mathematics of the system. Right. So then I'll use a numerical technique. So if I use a numerical technique, so this is the system. I've already written the MATLAB code for it. Okay, so the question says at t is equals to 100. So first I'll have to choose this as 100. Let me just show you that what kind of a behavioral change it is going to have. X label time, Y label position. Okay, now this looks fine. Now let me just see here. I've taken the step size as 1, and for now here in options I have chosen the relative tolerance and absolute tolerance as 10 to the power minus 10 and minus 10, which is because I want perfect answers. Now I'll just remove it. I'll remove the tolerances and I've taken the step size as you can see over here as 1. I'll compute the system. Can you see what kind of behavior it is showing? Straight line. It is showing that from 0.8 to around minus 0.1, it has come along a straight line. Is it possible? No, that is not true. Let me just change this to 0.1. There is already a hold on applied on it. So whatever the plot that I got, it is going to plot again on that. Now see. Can you see the behavior? How much change of a behavior? Let us first see it on the phase plot here. So blue one was for my time step when I was taking my step size as 1. So you can see that what kind of a prediction it was doing for my system. Okay, whatever my velocity was there, it underestimated my velocity. Right. At this point, this technique showed me that my velocity is somewhat here. If I assume at 0.4, it showed me that my velocity is less than whatever it is obtained over here. Okay, here my velocity is 0.994 and it is showing me a velocity less than 0.994. Okay, so it has underestimated the system. So if I would have taken my step size as 1, what would have happened? I would have designed my system that it is okay, it is going to maybe have a velocity v, but the system is actually attaining a velocity greater than v, right? So this can actually lead to a failure of the system. That is why it is very important that I choose my step size and tolerances in that way. If I zoom this area of my position, see here, it is showing me that the minimum position that my system is going to attain is anyways around let us suppose 0.7, approximately minus 0.7. It is going to attain this much of position in the negative direction. However, the actual behavior of the system is actually minus 0.76. And minus like 0.06, variation of 0.06 is not a very small amount. It is of a significant amount. Okay, like for 0.7, 0.06 is a significant amount. Almost it is 10%, isn't it? 10% of the variation. It is showing 10% variation in the whatever the maximum position it is attaining in the negative direction. So definitely it is very important that how we choose the step size. Now, if I consider it as 0.01, it is again going to plot it on that plot only. Now, if you see that from 0.1 to 0.01, the variation is not that much. However, now the plot is smooth. Whatever the plot that I'm getting, it is smooth. It was not that smooth earlier. See, can you see whatever the assumption that I was saying, that we are actually assuming that a small part of a circle is actually a straight line. This is what it is assuming. It is assuming that from here to here, we are connecting through a straight line. We are applying the technique in that way only. But now since I have divided the points from here to here into further 10 parts, so you can see that this has now become smooth. This has now become smooth. Okay, so this is how the numerical techniques work, and that is why we should always be very careful about our this step size. Now, as I told you that while choosing a step size, if I know that my system, if I know the analytical solution, then I can maybe choose the step size by comparing the solution with the analytical solution. But for a system when I don't know the analytical solution, and if I want to choose that what should be my step size. So what do I do? So here you can see that I chose the step size 1, then I chose the step size 0.1. The deviation was very major from 1 to 0.1. However, when I chose 0.01, the deviation was not that much. Okay, so I can conclude that okay, my step size I can choose it as 0.01. I can choose it at 0.01 even if I have to compute it to a very large number of iteration, let us suppose in lakhs of number, I can choose 0.1 also, because I can see that those 0.1 is not giving a very smooth variation, but the variation between choosing the steps as 0.1 and 0.01 is very less, so we can neglect it also in order to reduce our computation cost. Okay. Okay, so now we know that we want to have a step size of 0. Okay, I'll just give you an example also. Okay, here I have chosen the step size 0.01. This is the plot. I'll choose something like 0.05 and then I'll choose 0.001. Now see, now you can see that I have considered three values of step size and the variation is very minor, very, very minor. I can now neglect it. I can now neglect whatever the variation is. You see here, the variation, very small variation. Okay, so now I can neglect. So if I had an option of choosing that what should be my step size, I've compared for 0.001, 0.05 and 0.01. I can choose 0.01 because this is going to take less time and the variation is not that much. Okay. Now, what the question says is the value of x and y from the given system at t is equals to 100 is 0, 0 for the initial condition, 0.8, 0.8. So first I'll take this initial condition 0.8, 0.8. Okay. And let me just compute it. Let us see. Okay. Okay. So you can see that with time, my system has stabilized at 0 and its velocity is also 0. Okay. So the first option is correct. So my first option is correct. I'll write correct. Now coming on to B. For the initial condition x naught 0.1 and x naught dot 0.1. Okay, I'll just check. Okay, so this one also for this initial condition also my system has stabilized at 0, 0. So you can see when it is asking me that what is the value of the system, what is the value of x and y at t is equals to 100, I just have to see this, whatever the value is. Also, what I can do is I can find it like this also. I can write x, which where or z I should say z. Z is my variable. Now Z is the Z is having two data with itself. One is the position and the second one is the velocity. I'm constant. I want to know both the velocity and the position. So what am I going to do? I'm going to let Z into length of Z, comma is 2. See, when I write Z into length of Z, comma colon, what I mean is that if you remember that I can write rows and columns with my Z. So if I am writing length of Z, it is actually taking whatever the length is. If I write like this, okay, sorry, length of Z. So the length of Z is this value. Here you can also see. So this is the number of data points that I have considered. So what is it actually evaluating? It is actually evaluating the all the two values, which is the position and velocity at the last data point of Z. Okay, so here also I can see that these are some values into 10 to the power minus 7, which is very small value. So it is taking it as 0. Okay, coming on to second 0.1, 0.1. Okay, this was also true. Correct. Now coming on to C. My C is saying that it will be 0, 0 irrespective of the initial condition. Now this is a very big claim. How can I say that it is 0, 0 always? It is 0, 0 always if my 0, 0 is a if it is a stable fixed point, right? But if you remember this equation, I don't know whether people remember this or not, but this equation is the one which I considered in the I guess week 6 or 7 live session, and where we actually discussed about the bifurcation, kind of a bifurcation that was occurring in the system. And there was this Hop bifurcation, subcritical Hop bifurcation, where we proved analytically that there is a Hop bifurcation, and then we proved numerically that it is a subcritical Hop bifurcation. So, see, although I know, since we have already discussed about this question, but for now we consider that, okay, I don't know how this is going to be. I don't know if there is any kind of a bifurcation. So what am I going to do? The best way is I can numerically see. I'll consider some random points, random initial condition, and see whether it is true or not. Okay, for this initial condition also it is stabilizing. Okay, then let me change it to 1 comma 1. Now the system is not stabilizing. Now if you see, what did my system do? My system went to infinity. For the initial condition 1 comma 1, my system went to C. So straight line variation, it is going to infinity, which means that my system has now, what? My system has now become unstable. Let me choose it at 10 comma 10. See, again, it is going to infinity, which means what? Which means that up till a certain time, up till a certain initial condition, my system is stabilizing at 0 comma 0. However, after a certain limit, it is never coming back to 0 comma 0. It is going to infinity. So my this option C is not correct. And if you remember, as we discussed this equation in case of discussing about the bifurcation, there was a subcritical Hop bifurcation occurring, which means that my 0 comma 0 is stable up till my this here there was a parameter mu, which I've considered as -1, and here also there was a parameter mu, which I've considered as -1. So depending upon this parameter mu, if my parameter mu was greater than 0, then my system was having a spiral out behavior. 0 comma 0 was unstable, and as soon as my mu was becoming less than 0, my 0 comma 0 was stabilizing. However, there was an occurrence of a limit cycle where for mu less than 0, which was a unstable limit cycle, which means that if my system started at that limit cycle, it would always oscillate around or always like follow the circle. However, if there is a very small deviation from that limit cycle, it would go to infinity. And if my initial condition is inside of that limit cycle, since my 0 comma 0 is now stable, it is going to spiral into the 0 comma 0. Okay, coming on to question number 10. So my question number 10 says the logistic equation given as xn plus 1 is equals to r xn 1 minus xn. So I have to see about these things. Okay, so if you remember, I've discussed it in the overview slide also, that the logistic equation is given like this, where if I know that whatever the population is in the n generation, I can find out at the n plus 1 generation. Okay, so first I have to consider r 2.8. Okay, so here is the code. Okay, so I have taken the iteration up to 100, and it is asking me, okay, there is no time boundation. It is just asking me that what is going to happen in the steady state. Okay, so first I consider R 2.8. Okay, I think I forgot to mention over here. Let's write it. Take the take. Okay, we are taking the initial state as 0.1. So if I now compute it, let us see what is going to happen. See. Uh, for now, I am writing it like this. This is my, oh, no, no, no. This is my n, not xn. Okay. So this is my n and this is my xn plus 1. So here you can see that for the initial state there is some transient behavior. The population is actually fluctuating. However, the amplitude is reducing, and after a certain time it has attained a non-zero steady state. Non-zero steady state, that is, with the further increase of the iteration, the population is going to remain the same. Okay, so if I look about at my first system attain non-zero steady state for R 2.8. Okay, this is the correct option. So this is a correct option. Now second, system attain period 2 cycle for R 3.3. So if I consider my R as 3.3, here this is my R. If I consider this as 3.3, and after that I again solve this. Now if you see, now if you see here, if I, for example, consider this value, okay, so if I see that this value after one generation it is attaining this value, after two generation it is attaining this value, after three generation it is again attaining this value, and after four generation it is attaining this value again, which was the initial state that I considered. This was my initial, and again this was my initial. So you can see the difference between the generation. Here x shows the generation number, so 87 minus 83, which is 4. So you can see that for R 3.3 my system is actually period 4 cycle. After 4 generation the value is again coming out as the same. Okay, so the option that system attain period 2 cycle for R 3.3 is incorrect, because for R 3.3 my system is actually having a period 4 cycle. Okay, now if I consider for R 3.5, oh sorry, I took R 3.5 only, not 3.3. Okay, for 3.5 it is correct. It is a period 4 cycle. This is correct. My mistake, I took 3.5. However, okay, it's all done option. Coming on to 3.3. Okay, okay. So if you see for 3.3, there is some initial transient. And again, if you see that this is for 78. Anyways, after this, if you see, after one generation, it is attaining this value. And after second generation, it is attaining this value. So if you see 78 to 80. So if you see what is happening, there are two generations. After two generations, after 78, at 79 it attains a lower value, and after 79 at 80 it again comes back to the same value. So at my 3.3, my system is having a period 2 cycle. Okay, so this is also a correct option. So what did you see? You saw that for a logistic equation, if I change the value of R, my population growth is changing. Okay, so likewise, if you are now going to, like for example, if I just take a minute and change it to maybe 4, you'll see, what can you see? Is there any kind of a period doubling that you can see? I can see only chaos. Now this is a chaos. I'll just increase this. That is what I was saying, that though my logistic equation is a very simple equation, but it may lead to chaotic behavior. Okay, see, isn't it a chaotic system? Yes, it is. And so you can see that by the variation of R, my system could actually go to chaos. There's one, okay, yeah. Maybe let's just try for 3.3. This is the behavior for initial condition. If I change the initial condition to this, okay, I didn't apply, hold on. See, there is a phase difference. However, the values are still the same. While this will not be the case in case of a chaotic system, because in a chaotic system, a small change in the initial condition is what? It is going to have a significant impact on the final, so significant variation on the final state. See, now you can see the variation. Initial was same almost, but after that it diverged a lot. Okay, so this is what your logistic equation, which is a very nice example. If you get time, then please study about this logistic equation. It is going to tell you like how period doubling is actually happening, how period 2 oscillation is happening, how period 4 is occurring from period 2 and everything. It is a very basic example which we take for a discrete system. The only difference is that it is a discrete system. We usually deal with uh, continuous system when we are finding out the dynamics of a real system. And this is actually a discrete system. However, this gives a very good example of how the system is transitioning with the change of R. Okay, so okay, this was it for today's live session. And if you have any doubt, you can ask. If you have any doubt which you get while you are studying, you can ask in the next live session. And with this, I guess we have completed majority of our live session. So this was week 9. We have only three live sessions left, and I'll be taking an additional live session at the end. So if you have any doubt regarding the subject, regarding the application of the course, and how can this course be helpful for you for further application, you can definitely ask me. And I would really appreciate if you have any doubts. And that is it. Also, since I have told you about the numerical technique, I would appreciate if you could just solve and give a basic like practice about the numerical technique and maybe learn how you can actually write a numerical technique in MATLAB so that you can do iterations, hundred and thousand of iterations, and then you can maybe, or maybe you can use the one or two iteration and you can see that whatever you computed on your own, whatever when our MATLAB is computed, how much is the error, much is the accuracy of MATLAB, how much is your accuracy. That would give a good practice, and it would also help you to develop your intuition about finding out the roots or all those things. Okay. So this is it for today's live session. Do you have any doubt?
No, madam. Thank you.
Okay, thank you so much. I'll end the meeting now.